Hello everybody, this is Chapter 4, Section 3. We're going to be dealing with electron configurations. You do need a periodic table handy. We're going to use it multiple times today. So starting off, we're going to look at a few rules. The first one is the Pauli exclusion principle. So there is part of its definition. There are two parts to it. It says each orbital can hold two electrons, at most two electrons, then they must have opposite spin. The opposite or the other part to the Pauli exclusion principle is no two electrons can have the same four quantum numbers. No two electrons can have the same four quantum numbers. So Qn is for quantum numbers. In the previous section, we went over what those quantum numbers are. If you remember, it was the principal quantum number, the magnetic quantum number, the spin quantum number, and the angular momentum quantum number. So, getting back to the Pauli exclusion principle, the box itself, so if we highlight this box, the box is going to represent an orbital. And with the different types of notations we're doing, we're going to see the box more today. And each of the arrows, so your up and down arrows you have here represent your two electrons. If the arrow is pointing up, we're going to say that it's spinning clockwise. If it's pointing down, it is spinning counterclockwise. And we will get to the two electrons have an opposite spin. Just quickly here, your electrons, they have the same charge. If they're living in the same spot, they want to repel each other. But when they have an opposite spin, it creates a magnetic attraction. That magnetic attraction is going to override the electrical repulsion that they have for each other due to their like charges, but the opposite spin will help that. Next up, we have the off-ball principle. The off-ball principle says the electrons will fill the lowest energy orbitals first. And we're going to go through a few representations of how you are going to remember order of energy filling or order of electron filling going from lowest to highest energy for the current periodic table. We also call this the lazy tenant rule. If you were living in a 3-story building and there was not an elevator, most people are going to want to live on the first floor, not the third floor. We'll say due to laziness. Electrons are the same way. The lowest energy is going to be whatever is closest to the nucleus. So as I'm looking at this right here, closest to the nucleus is that first energy level. First energy level. Remember, for energy level, we use the letter N, so N equals 1. And electrons want to live there. But once that is filled, they have to move up to the next energy level. This particular drawing or figure is showing you the order in which energy is filling. So it starts here at the bottom with 1s, goes 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, and you can see that we are starting to go not quite in what seems like a logical order. And we will talk about why that is as we go. But there are a couple ways in which when we have our test or our quiz or you're doing your homework, you need to know the order of filling. We're going to look at a couple of other options for you to remember this order of filling. The first one we're going to do is actually my preferred method, only because when we have tests for electron configurations and multiple other tests, you're going to have a periodic table to look at. If you have a periodic table to look at and you can remember a few things like period numbers and blocks, you should be able to follow it about like an old manual typewriter, left to right, left to right, left to right. So the first few things I'm going to look at is going to be parts that you should already be aware of. We know that this is the S block, so I will label that up above it. So S block here. And in the middle, we have the D block. and we'll label that too as we go. Off to the right side, we have the P block. It's taking me a minute to pick out some different colors. And at the bottom, we have the F block. Now, if I go back and I highlight what my group numbers are, or my period numbers off to the side, period 1, 2, 3, 4, all the way down through 7, periods run left to right. And like I said, manual typewriter, that's what we're going to do. That helium really belongs right here next to hydrogen, because helium is supposed to be part of the S block. But we do have it over there with group 18, your other noble gases, because its properties are going to be like your noble gases. So starting off, as I'm filling up, we start in the top left. Again, energy level 1. And this first section represents 1s. So all of this is 1s. If I move to the very end, well, that helium's already taken care of, so we now move down to our second row. Next up, this section is called 2s. When I move over here, I do hit the end of the second row, and this section is called 2p. I've reached the end of the section, so now I'm ready to go to the next row, and this is 3s. Moving on over, this section is 3p. Hit the end of the section, go to the next row. This is 4s. When I hit this section right here for D, we actually have to take the energy level and subtract 1. And that energy level, hopefully you've noticed, matches with the period number. Matches with the period number. So I take the 4 right here, subtract 1 and get 3, so that section is labeled 3D. After 3D fills up, my next section is back to 4P. So again, with the P and S sublevels and those blocks, you do not subtract anything. When we get down to F, you're actually going to subtract 2 when you get down to F. So this section, lanthanum through YB, I don't even want to attempt to pronounce it, but these belong right up here between group 3 and group 4. And I'm going to change my colors. The actinides are going to belong right here. So the lanthanides, that's your top set series. The actinides is your bottom series. And these would be labeled, since this is really part of period 6 and this one is part of period 7, this would be 6 minus 2 is 4, so this would be 4F. And the next one is 7 minus 2, which is 5. That would be 5F. So again, if you could follow the periodic table along, you can get each individual section. We're going to go look at another way to look at this too. This is called the diagonal rule. To me, it kind of looks like a mini tornado. And you can see this diagonal rule exhibited multiple ways if you were to look online. But again, it all starts with you labeling. So if I were to create this myself and set up some labels, I'm going to move this over. I'm going to start right here, 1S. Whoop. 1, 2, 3, 4, 5, 6, 7. So those 7 represent the 7 periods. The S block is first as far as order of filling. And then we're going to drop down to the P block, which doesn't start until period 2. So again, labeling all of these numbers again. Put a P on the back of each of them. And Now I'm moving on over. For the D block, which is next, that starts on period 3. So we will get our period 3 through 7 here. That's the D block. Notice they don't have it labeled there, but you can easily put it there. And then for the F block, we've just talked about 4F and 5F. That's why you see 4F and 5F listed. So again, 1, 2, 3, 4. And labeling both of those F. So if you were to recreate this on your test, that's the good starting point. And then you can see with the red lines that they have going. I'm just going to put start right here. And we go through 1S. Come back up, 2S. And then you keep going back around to the top. 2P, 3S. 3P, 4S. 3D, 4P, 5S, and you can see that things are not going in order the way you expect it. 4D, 5P, 6S, 4F, 5D, 6P, 7S, and then 5S, 6D, 7P. That ends the current periodic table that we have. There are hypotheticals out there. If we find some more elements, there are more energy levels than just going to the 7th energy level. So again, that's the diagonal rule. Write it down. Make sure you understand how to get to this order of filling. The next rule we have is Hund's rule. So within a sublevel, you have to put 1 electron per orbital before you pair them up. If we go back and we remember some of the math that we had worked with here for sublevels, our sublevels, we have S, P, D, and F. The number of orbitals that you have per sublevel. S sublevel has 1 orbital, P has 3, D 5, and F 7. So when I say number of orbitals, that's how many boxes you could draw. So S just has the 1 box, P would have 3. So you could draw it out like this. D would have 5. And then F would have 7, just the 1 box there for S. So within each of those boxes, that's how many electrons can fill there. We can also add on to this your number of electrons, just so that you're aware, trying to tie this back into section 2. If S can only hold 2 electrons, again, 2 electrons per orbital, 1 times 2 is equal to 2. 3 times 2 is 6. Again, Hund's rule is saying you have to spread them out first, and then if you need to, go back and double up. 5 times 2 is 10. Again, Hund's rule says you need to spread them out within that sublevel first, and then you can go back and double up. So we're going to start with up arrows for clockwise, down arrows counterclockwise, and that's pretty much as specific as we're going to get about that. So we call it the empty bus seat rule. For the empty bus seat rule, if you had 20 people getting on a bus and there were 20 seats, more than likely they are going to want a seat to themselves so they can stretch out, lay down, chill out, whatever it is they're going to do. Electrons are the same way. They would much rather, if there are 3 orbitals available, such as the one in this case, they want to spread themselves out first before they have to go back and double up. So the picture on the right is the correct picture as far as orbital filling, and that does obey Hund's rule. Now, we've got 3 types of notation that I want you to know. The first one, they're calling it an orbital diagram. I often refer to it as orbital notation. This is where you have your periodic table handy. And when we look at this, the example they're given is oxygen. So if I told you go write the orbital notation for oxygen, the first thing you would have to do is know how many electrons you're dealing with. We have 8 electrons that we are dealing with. Instead of me drawing a box, I am going to draw an orbital line. So there it is, an orbital line, instead of the full box. And with the orbital line, underneath it, I'm going to label, you have to start with the lowest energy sublevel first, which is on energy level 1, S sublevel. And S sublevel only has one orbital, but we are going to fill it up with 2 electrons. Got to find a home for 6 more electrons. After 1s is 2s. Again, go find one of those pictures we were looking at for level filling, whichever one works best for you. There it is. Next is 2s. Again, an S sublevel only has 1 orbital, so there's the one line, but it can hold 2 electrons. Great. Now we've got to find a home for 4 more electrons. After 2s, what fills up? It is 2p. Okay, the p sublevel has 3 orbitals, so you must show all 3 orbitals, represent them, label them, even if an electron does not go into each of those orbitals. But once 1 electron goes within to that entire sublevel, you have to represent the whole sublevel. We need 4 more electrons. Hund's rule says you've got to spread them out first, 1, 2, 3, then go back and double up. We've doubled up. If you count the total number of electrons here, you should have 8 electrons. That is the orbital notation for oxygen. Let's go do the orbital notation for sulfur. So find sulfur on the periodic table. I'm looking at it. It has 16 electrons. Again, you're looking at the atomic number to find number of electrons. Start with the lowest energy sublevel first, 1s. Again, an S sublevel has 1 orbital, P has 3, D has 5, so we can only do 1 orbital line. It holds 2 electrons. After 1s is 2s. Again, just the 1 orbital holds 2 electrons. After 2s, what fills up next? 2p. We're showing all 3 orbitals within that p sublevel. Please make sure you know the order of filling. So we're spreading them out first, then we're going back to double them up. There went 6 more electrons. Still got to find a home for 6 more. After 2p, what fills up? 3s. Again, that S sublevel only has 1 orbital, 2 electrons. And after 3s is 3p. Must represent all orbitals for a p sublevel. We need 4 more electrons. 1, 2, 3, 4. That is the orbital notation for sulfur. The next type of notation is electron configuration. I'm going to erase some of this over here. With electron configuration, we're going to start to condense what we're looking at. So to make it easy, 1s, it has 2 arrows. We do a superscripted 2. 2s has 2 arrows, another superscripted 2. 2p, we're going to put that whole sublevel together, and in total, it has 6 electrons. So there's where the superscripted 6 is. 3s has 2 electrons, and again, 3p, put it all together, has 4 electrons. This is called electron configuration. That is the second of 3 types that we're going to look at. So that is electron configuration. And going back to this example with oxygen there at the bottom, the electron configuration for oxygen is 1s2, 2s2, 2p4. So again, it is a condensed version of what orbital notation is. So again, so far, orbital notation and electron configuration. Now we're going to move on to noble gas notation. In the PowerPoint, it's called longhand configuration, but you will hear me refer to it as noble gas notation. So now we're heading back to sulfur with its 16 electrons, and we're going to show you the noble gas notation. So again, I'm going to refer to it as noble gas notation. We take the abbreviated notation that we had earlier. Going to go ahead and write out, longhand configuration. I've totally said the wrong thing. Longhand configuration is electron configuration. So let me at least erase what I just put right there. So electron configuration. And this is what we had for sulfur. And now we're going to go to noble gas notation. Within the noble gas notation, which is also called shorthand configuration, we're going to abbreviate the core electrons or inner shell electrons from valence electrons. If I go back up to our example, your outermost electrons or valence electrons are going to be in your highest occupied energy level. So there's a new phrase for you. Highest occupied energy level. 3 is the highest occupied energy level because we have energy level 1, 2, and 3. So these right here are considered valence electrons. And valence electrons live in the highest occupied energy level. The rest of the electrons are considered to be core electrons, or also known as inner shell electrons. So those inner shell electrons are the ones that we are going to shorthand up. If you go back and you look, I think my podcast kind of timed out there for a second. So again, the noble gas notation. Ooh, it looks like several things are missing that I thought I'd already said. So these right here are core electrons. I see the word valence is missing over here. So those were valence electrons off to the right, and they belong in your highest occupied energy level. Core electrons, also called inner shell electrons, are the next abbreviated part that we're going to do in noble gas notation. If you count up the number of electrons that you see there, right here, 2 plus 2 plus 6 is 10. Element number 10 is neon. So I will abbreviate it with brackets, the symbol for neon. And again, we use uppercase and lowercase letters appropriately. And now I'm ready to put on the rest of my valence electrons, which is 3s2, 3p4. So again, neon has 10 electrons. We have 2 more here, 4 more there. Add all that up, you get 16 electrons, which is how many electrons sulfur should have. If we go back and we do the noble gas notation for oxygen, which is one of the ones we were looking at earlier, oxygen had 8 electrons. And again, if you're looking at the periodic table, the core electrons for oxygen is on the second row. I'm going to show you another way to look at this too. I'm going to find oxygen, right, pick a darker color, right here. The noble gas that comes before it, and again, noble gases are all in group 18. Group 18. You need the noble gas that comes before it, so you go up one level over to the noble gas, that's helium. That is what gets abbreviated, helium. And now we start on the row that your element is on, in this case, row number 2. You hit the 2s first, 2s, we fill up 1, 2. And then we are going to hit 2p. And you go over 1, 2, 3, 4. It is the 4th element over within the p block. So that is your noble gas notation for oxygen. Here's another depiction of what I was showing you earlier. Again, you don't have all the filler of the periodic table as far as names, atomic numbers, atomic masses, element symbols, but you can see as we go through the order in which they fill, 1s is first, because there's your helium. Then we have 2s, 2p, 3s, 3p, 4s, 3d, 4p, starting back over, 5s, 4d, 5p, because remember for D, we subtract 1 from whatever our energy level is, which is also the period number, and you continue on from there. So again, period number represents your energy level. So you've got 7 of those. We are ignoring the AB group number, and then the columns within your sublevels tell you the number of electrons in the sublevel. So if we are group 1 or group 2, that's 1 or 2 electrons within S. Group 13, that would be 1 electron in P. Group 14 would be 2 electrons within P, because we're counting over within the group. And this right here, for an example of hydrogen, you have 1s1. The large number out front represents the period that it's on and also the energy level. We've got the block, and then this represents the column within the block. So it's the first column of the S block, so S1. Again, shorthand configuration, also called noble gas notation. Your core electrons, we do go up 1 row before we move over. I showed you that previously. And we'll look at an example with germanium here. For germanium, you go up and over to group 18. That element is argon, so you abbreviated argon. Now we're ready to go to the row that germanium is on, so the 4th row. We start with 4s, so 1, 2. Then we go to 3d. There are 10 of those. That is 3d10. And then we pick back up with the P block, so 4p, it's the second one, that is 4b2. Now, the correct way, once you start getting into these D blocks and we are rearranging your final answer for this, because we want to group our energy levels together, the 3 is lower as a whole, 3d10, 4s2, 4p2 would be your final answer. And now we're going to look at stability. So, full energy levels, that's our noble gases, create stability. Full sublevels, so that is group 2, group 12, and then the end of the F block. And half-filled sublevels create a certain level of stability. So we're going to go look at an exception. Copper. If we were to write out the configuration for copper, again, you're looking at your periodic table. Find copper. If you go up and over, you expect it to be Ar 4s2 3d9. So this is copper rewritten, again, getting the 3 down there with argon, because within argon you have 3s and 3p already there, and then the 4s on the outside. But find copper on the periodic table. Notice it is really close to being a full sublevel. So what happens is copper, and copper is in group 11, will take an electron out of 4s, pull it into 3d, so the real configuration ends up being 3d10 4s1. And this gives us a full sublevel. So any of those elements in group 11 will make that exception. They will pull from the higher S sublevel into the D sublevel to fill it up. The same thing is going to happen with group 6. So again, looking at chromium here, and this will be for any element within group 6, there is the expected configuration. Again, swap the D and the S. Oop. But because a half-filled D sublevel, half-filled meaning it would have 5 electrons, because half of 10 is 5, we have the same thing happen here. Sorry about that. So D sublevel is going to pull from S, and the final answer would be 3D5. And again, that 5 is going to be a half-filled D sublevel for S1. So again, group 6, group 11, this gives us a half-filled sublevel, which creates stability. Group 11, whenever they pull out of S, gives it a filled sublevel, which creates stability.